So I was saying basically the students who need to be with us are not with us. Those students who were actually surprised by the exam. Some students are actually surprised how come there's data analysis in the exam. You guys, it's very important for you to know that objective number 1 of physics lab is not physics. It's actually physics lab. Am I connected? Because this is not, the green point here is not showing to me. Can you hear me? I know I'm connected. I'm just checking.
Yes, we can hear you.
All right. Now I'm having like connection issues with my brain after this connection problem I had last week. Anyway, so a lot of students are surprised because the midterm was full of data analysis. Let me know the final exam is going to be even more full of data analysis. It's not about physics, and many of you know this by now. It's about analyzing your measurements and your data, okay? So the content, the plan for today is to discuss lab 6. We have nothing else on our agenda because lab 5, you're done with it. And lab 5, you're done with it, and we're done with the midterm, and I showed you your final grades. And also I need to say sorry for the students who emailed me. A lot of students in your class did email me concerning the midterm. I took all your discussions into account, and I did not reply to your emails because I needed time to think what to do and how to raise your grade. And now that I gave you back your grades with a raise, probably I would answer all your questions. So if you still have issues, please let me know. I'm definitely not talking to Fadi, not talking to Rima, not talking to Carl, and not talking to Leia. The students I need to talk to are the students who are not with us, unfortunately. Now let me put the participants on just in case somebody would join so I can tell who's with us and who is not with us. All right, lab 6, centripetal force, that's lab 6. The theory is not straightforward, and the experiment as well, but probably the theory is easier than the experiments, saying that the experiments may not look clear at the beginning. I will try my best to make it as clear as possible. Also, the video I recorded is not great. I was planning to record another video for you because I did not like many things in the video that I recorded. I may not be able to, so I'm gonna share with you the old video anyway, and I'm gonna watch it again. If I believe that it's not clear for some reason, I can share another instructor's video as well. So you can have 2 videos in case you believe you have some questions, okay? I was not happy with the fact that the setup itself was out of the scope of the camera, and probably this will make you more confused. To discuss the centripetal force, I'm gonna discuss first of all acceleration. So I need people to remind me how you define acceleration. So you speak up, please, to define acceleration. How do you define acceleration?
Derivative of the velocity over time in function of time.
Of the velocity as a function of time. I cannot say no, but I can say this could be Chinese for a lot of students. Can we find an easier way to say it?
Is it the change in velocity?
Change in velocity. I'm going to change it a bit and say rate of change in velocity. All right? Why rate of change? Basically, rate means divided by time. Okay, so the change in velocity alone is v final minus v initial, and that will not give you acceleration unless you divide by time. So the rate of change is how fast the change is happening. All right, now I need someone to explain what velocity is. So we're talking about velocity in both statements, right? So I need someone to discuss what velocity is. And thank you for helping out.
Rate of change in displacement.
Yeah, you can say that, and probably I can use something easier. What's velocity?
Distance over time.
Yes, can you use more English and less math? speed.
The speed of.
All right. Is that accurate? Can I say velocity is equal to speed? You're very close, but you're not very precise. Let me say you're not very accurate.
The speed in a certain, I don't know, direction, maybe.
All right. Probably we can add a direction. All right. So now velocity is speed and direction. And I need someone to break down the idea of speed. Speed is what? How what? How heavy? How long? How boring? How what?
How fast?
How fast, or probably how slow, right? So let me use this, how slow. So we were actually discussing, trying to dissect what acceleration is, the derivative of velocity as a function of time. I should write with respect to time, yeah. And I can say it's the rate of change and velocity, rate at which velocity is changing. So both can be said. Velocity is speed and direction, and speed is how fast and how slow. All right, so which means I have acceleration only when the speed changes, because we're talking about the change, and when direction changes. Can you give me an example where the speed is changing? I need an example where the speed is changing. Any silly example from daily life.
Can we say a car moving at a speed of 5 meters per second, then it changes to 10?
Yes, speeding up on a highway. And can you give me an example of something slowing down?
No, the initial, it was moving at 10, then it slows down.
Yeah, you see a cat 5. And you don't want to hit the cat. You slow down to a stop before hitting the cat. All right. Any example of give me an example where the direction is changing. You have a roundabout and you have cars around the roundabout and they're actually moving in a circle, right? Or you can simply think of Earth and you have a satellite around Earth, orbiting Earth, you know? So this is a change in direction. Do you agree? Probably you're talking in the chat. I want you please to respond.
Yes, yes.
All right. Fine. All right. So now we know any example where you're speeding up or slowing down or changing direction will show you a change in velocity. So it's going to give you a certain acceleration. All right. These are examples where like comic, where this is speeding up. So it's accelerating. This is slowing down. So it is accelerating. And this is changing direction. So it is accelerating. Keep in mind that you have case 1, case 2, and case 3. Those two will give you the tangential acceleration, and this will give you the normal or the centripetal acceleration. Let me insert a text box and writing it down. Do you think I can write it if I move those a bit? So this is called the tangential acceleration. Let me make it a little bigger like this. Okay. Tangential acceleration is the one that would speed you up or slow you down. And this one is gonna be called centripetal acceleration. What do you call it in the course? Yes? Centripetal acceleration. Do you call it centripetal acceleration or normal acceleration? Please respond to me.
I guess we're not taking them in the course.
Okay, so you did not do that in the course yet. Did you ever do that last year? Change in direction, or was it only?
Yes.
Okay,
and it's normal acceleration.
Okay, you used to call it normal. All right.
Yes.
So normal or centripetal means the same. Basically, the centripetal acceleration, if I take into consideration this object, by the way, this object is moving at a constant speed. And by constant speed, so let me write this down, you have a constant speed. It's not speeding up, neither slowing down, it's only turning around the circle. All right, the centripetal acceleration is towards the center, and that's why we call it centripetal. This is where the center is. You see, all the acceleration are pointing towards the center, you see? We also call it normal acceleration because normal in math means perpendicular. So the acceleration is perpendicular to the motion, perpendicular to the motion. And since the motion is tangent to the circle, perpendicular is the radius. So any perpendicular to the motion would be the radius. So any normal will be centripetal, if I may say. All right? To find the tangential acceleration, you do V final minus V initial over time. The centripetal acceleration is different. You cannot do V final minus V initial over time because V final and V initial are equal in magnitude, and if you find the difference, you get 0. To be able to find the centripetal acceleration, and please let me know if you ever saw this in high school, you do V squared over R. Have you ever saw this equation in high school?
Yes, and we call it normal.
All right, we used to call
Yes.
it the normal acceleration. Okay, so it is related to speed because the faster you are, the greater the push should be to turn you. And the smaller the radius, the greater the push should be to turn you as well. And you can feel it in your bodies. Imagine you driving on a highway and suddenly you need to do a U-turn. You can feel your body projected outwards. And this is proportional somehow to the centripetal or the normal acceleration. Nazih just joined us. Nazih, so in your absence, we talked a bit about the midterm, we talked a bit about the experiments coming and how to get ready for the final exam. And we discussed how we raised the grades for the midterm and what it means. And now we're discussing lab 6. The part that you missed, you can easily watch it again on the recorded session. Is it okay, Nazih? I don't know if Nazih can hear me. I assume he can or probably cannot. Anyway, if you have any question, Nazih, you let me know. So the centripetal acceleration, usually you study it at the end of kinematics. So the only way to find it is V squared over R. Now I need to discuss the centripetal force. And jumping, I had a slide in here. What happened? Okay, let me insert it again. It was the last picture. Probably I did not save the file. This, yes, this is why I inserted. Okay, where is it? This is my dear picture. So to be able to find the force, I can use the relationship F equals ma. That is Newton's, which law? First, second, or third? Do you remember?
Second.
All right, so I will use Newton's second law to be able to find the centripetal force or the force responsible to turn me around a certain point. So since the acceleration, and I want you to see it in here, is V squared over R, the force is gonna be M times V squared over R. If you want, you can simply forget about this one because it discusses the angular speed. Just forget about it, okay? Why is my screen being delayed? It could be from the Zoom recording. All right, so just think of mv squared over r. The centripetal force and the centripetal acceleration should be pointing in the same direction. All right, this is also another diagram that shows you that the centripetal force is mv squared over r, meaning the bigger the velocity, the bigger the centripetal force. Like, for example, if this whoever satellite, or let's say it's a cat going around a tree, and this is the tree, and the cat or the dog is attached by a wire. The faster the cat, the more force you need in the wire to be able to maintain circular motion. And if the cat is, the dog is really fast, probably he's gonna break the wire because the force is gonna be really high. On the other hand, the bigger the radius, the less the force, because if the length of the wire is really long, you need less force to be able to pull your dog in a circular position, you know? It's okay, Nazia. If you have questions, just stop me. All right, so this is now the centripetal force. Now you're set up. And after the setup, I need to discuss the procedure in the video. All right? The setup is really a big thing. I will try my best to explain it. I hope really that you don't get confused. Let me show you what you have. You have a stand. So let me use this to explain that I have a simple stand in here. Okay, you will see it in the video. On the stand, you have a rotating platform. It's a platform that is super horizontal. Rotation happens around this rod, and you can tell that friction is very well reduced. How do I know? If I just push the rotating platform with my finger, it's gonna rotate horizontally, and it's not gonna stop anytime soon. I can tell friction is very low, all right? And it's very beautiful to look at. In the center, you have something called center post or central post. Inside the central post, you have a spring. So probably you cannot see it. Let me grab a very thin pen to draw the spring for you. And you will see it in the video in a moment. You have a spring in here. And then you have a orange disc. Then you have a wire. You have a pulley. And it will go. All right, this is your system. The system, the mass of which is known. So this is the system you're gonna look at. So when rotation is happening, this is the object that is gonna rotate. So when I do mv squared over r, I take mass of my system and the radius of my system, and this is the radius of my system. Okay, I need to measure it with a regular ruler. And what is the error on a regular ruler?
.5.
How do you know? And what's the unit?
It's the smallest subdivision divided by 2 millimeter.
Okay, so 1 millimeter divided by 2 is 0.5 millimeters. So all my answers in millimeters should have 1 decimal like the error. Thank you so much, Car. I really agree with this. All right, this is called the slide post assembly. So here you have a post. What's interesting about the post is that you have a wire that would be attached to your system. So now your system is attached by wire 1, wire 2, and wire 3. On wire 3, you have a hanging mass. I'm gonna call it small m, and let me call this one big M, the mass of the system. Okay, and this is small m. When I attach small m to my system, it's gonna create a force in this direction that I'm gonna call tension. So now I have this tension and this tension and this tension. I need to look for equilibrium. How do I create equilibrium? Add enough masses, move this a bit in such a way for this wire to be vertical and the two wires to be horizontal. Okay? When I'm ready to do the experiments, I'm supposed to remove this section. Yani, remove the wire, remove the pulley, remove the hanging mass. Definitely, because of the spring that is here, this will go back to this position. All right? Now my job is start rotating the platform. I need somebody to tell me what happens to my system when I rotate the platform. Do you think it's gonna move, yes or no, and how? So imagine you are attached to a wire and the wire is flexible because of a spring. And I rotate the platform. What happens to my heavy object? Does it slide outward or inward?
Outward?
I think outward.
Yeah, it's gonna go outward. I'm gonna keep on pushing the rotating platform until I reach a speed where the system will reach its initial position. All right? I would say the rotating platform created a centripetal force equivalent to the old tension because it gave me enough push to go back to my equilibrium position. How do I find the centripetal force? I do M, the big system, M, V squared over R. How do I find the tension in the wire? Who can tell? The tension in the wire. How do I find it? Isn't the tension equal to the weight of this guy? Yes or no? Michelle, it's good you
Yes.
just joined us. Michelle, you're too late. Missing 30 minutes of the session is like missing the whole session. All right, so I need someone to explain to me how can we calculate the tension in the wire? So you have a wire, a pulley, and then you have a hanging mass. So how do you find the tension in the wire? Isn't it the weight of the hanging mass? Yes or no?
Yes. Yes.
Okay, how do you find the weight of the hanging mass? What is
We
your
have
weight?
it.
Yeah, we know the mass, not the weight. How do you find the weight?
I forgot.
Okay, what's your mass card?
MG.
It's M times G. Thank you so much. Is that you, Leah? The weight
Yes.
is M times G. All right, so be careful. M is the mass of the hanging weight. And this big M is the mass of my system, because I'm talking about my big system rotating. My system is around 200 grams and the hanging mass is around 40, 50 grams. It's gonna be given to you. All right, now I have a question. How do I know that my system went back to the same position? It's tough. This will be rotating fast. How do I know that this went back to the initial position? Actually, you won't be able to answer this question because there's something here. You see this black level? This black level can be moved and you can put it, like for example, you put your system at this position, you put the black level at the orange spring, and then you remove the pulley, and this will go back to this position and the orange thing will go up. Then you start rotating. Whenever the orange disc will go back to the black level, you can tell that the system went back to its initial position. This is one. Two, now it's your turn to be creative. If I give you a stopwatch, do you know how to find the speed? Speed, not the velocity, like the speed, the linear speed of your system. So you have a system rotating, and this is the rod or the platform viewed from above. So it's gonna rotate in this direction and in this direction, and the system is somewhere here. So it's gonna do these rotations around the center, and this is the radius. So this is again viewed from above, like a helicopter view. So the question is, how do you find the speed of your system? This is your system. You have a stopwatch and a ruler. How do you find the speed? How do you find the speed? What is speed by definition?
We measure 2 times and we divide over delta t.
I like this. Must measure which time basically? Time to do what?
The place of the object at t equals مثلا 2, 4.
Okay, so at time 2 seconds, you find the position, and time 4 seconds, you find the position. Let's say here. Okay, but how do you record the distance? This is rotating so fast, you know? Can you tell me how far is one rotation? Yeah, how many centimeters? If I do one complete rotation, it's how many centimeters?
Do we have the radius?
Yes, we have a ruler. We can measure the radius.
2 pi r.
Okay, 2 pi r is the distance covered. Okay.
Yes.
Can we time one full rotation?
Yes.
It's a bit tough because it's very fast. Probably we can time 10 rotations and divide by 10. Yes. So if 10 rotations will take me 10 seconds, I can tell that one rotation is 1 second. All right. So you do distance over time. And time is, so the distance is 2 pi r, the time is 1 period. And for you to be able to find 1 period, you time 10 different rotations, and then you multiply, you divide by 10 to get the period, okay? And this is gonna be equal to V, the speed. Now let me visit the lab report a bit and see if we can answer some of the questions. So the lab report is here next to us. They want you to calculate what is the mass hanging over the pulley. They're talking about this one. It's gonna be given to you. All the masses are given in digital form. I mean, using a digital measuring tool. The weight of the mass hanging over the pulley is equal to the centripetal force. Calculate this force. Leah, right? Leah just did it for us. Fill your data in the table below. I'm gonna give you the radius and the time taken to complete one cycle. I do the measurements for you and you complete the table. Plot the radius versus the square of the period. This is the radius, y-axis, this is the x-axis. Draw the best fit line through the data points, calculate the slope. I need someone to explain to me how I find the best fit line and how I find the slope. How do you do it? Anyone?
Can we use Excel?
Of course you can use Excel. And how do you do it on Excel?
We plot the points, I think.
All right, let me just jump to Excel. I know for a fact that some students don't know how to do this, and I'm more than happy to do this again. All right, I'm just opening a new, all right, this is X and this is Y. I'm gonna show you some random values, 1, 2, 3, 4, 5. And then here is gonna be 10, 20, 30, 40, 50. Just the random values for you to be able to know how to plot. You select the values only, make sure X first, then Y, and then you do insert, scatter. You make sure to change the title, and you can add chart elements like label the axis and add a unit, and you can change the color of your graph. And when you finish, you do right click, add trend line. The trend line is the best fit. Do you see it? And now if you move those away, our names, you can see here something that states something about the trend line. You can say linear and display equation. When you say display equation, it will give you the equation directly of the best fit. All right? Yeah, just let me put this away. All right, this is the equation of the best fit. Let me select what's inside and let me make it a bit bigger for you to see it. This is the equation of the straight line. Now from the equation of the straight line, can you tell me what is the slope? Exactly, because we say y equals bx plus a, right? I'm just following your Casio calculator because it doesn't say ax plus b, it says bx plus a. So if you really look into this one, and if I make it bigger for you to be able to see it, and if I use a pen, this is your slope. Anything that is before x is the slope, and this is the y-intercept. So everything you have next to x is the slope. What is the unit for the slope? It's gonna be the unit of your y over the unit of x. Now going back to our case, what is the unit of y when you plot the radius versus the square of the period? That's the y and that's the x. Can you help me with the units? What's the unit of y?
Meter.
You can say meter. And what's the unit of x?
Also meter.
No, square of the period.
Oh, meter squared. So
What is
it's
period?
meter.
Period is the time. Let me add it. It's the time for one full cycle. So period equals the time
Seconds.
for one full cycles. Yes, it's gonna be in seconds. And now that you know it's in seconds, what is period squared? Because it's the square of the period. So they said the square of the period.
Second square.
Exactly. So y is meters and x is gonna be seconds squared. Let me write it down. This is, where's my pen? Seconds. Yeah, Allah, it's not writing well. All right, parenthesis seconds square. So now your slope is gonna be, where's the slope? This, yes. What is the unit of the slope in this case, which is here? It's gonna be meter divided by seconds squared. Okay, let me take a screenshot of this one and keep it somehow in our document to keep. All right, so probably insert a new slide at the end and throw our screenshot here just in case we need it for later on. Okay, where is it? Is it? I think it's too big. I'm gonna rescale it later. Now back to our document. We know how to find the best fit line and we know how to calculate the slope. They want us to deduce something from the slope. And here I need your help. How is R and T squared related? I'm gonna fetch a document, but I need your help. I need people like Leah and Carl and Michelle and Nazih and Rima and Fadi to help me come up with equations related to this lab. What equations did we use so far? Any equation you remember? The centripetal force, what was it? Yeah, 2 pi r over t, what was it equal to?
V.
Okay, this is one equation that Carl just gave me. Who remembers the centripetal force equation?
V squared over R.
Okay, mv squared, we need to be careful. It was capital M, the system, v squared over r. And can I say that this was equal to the weight of the hanging mass, which is small m times g?
Yes.
Okay, now can I replace v by all this? Put it in here. I'm not sure I'm gonna reach something reasonable. I need to try. So let's try it. It's gonna be big M times, instead of V, I'm gonna write 4 pi squared R squared over period squared. Okay, sounds so big. Divided all of it by R. Okay, and all this is equal to mg. Okay, and now we need, remember, we're plotting again. What was it that we're plotting? The radius versus period squared. So I want you now to take this equation and write radius alone. By the way, you can see that this and this cancel out. So radius alone and t squared alone. You want to try? Radius equals. So it's mg. Then I'm gonna divide by 4 pi squared big M. 4 pi squared big M. And eventually t squared, am I right? Let me check again. So this one would go, I'm simply cross multiplying. So R is this times t squared divided by, yes. So when I plot R versus t squared, this is gonna be the slope because this represents Y and this represents X. So this is gonna be the slope. Okay, slope. Oops, I just messed up my, I'm just undo, yes. So this is gonna be the slope. Okay, I like this. Now they want you to use the slope, and let me take a screenshot of this and keep it in our document. They want me to use the slope to find what? The mass of the system. What was the question again? Deduce the centripetal force from the slope. The centripetal force is mg, so it's here. They want the mg, all of this. So instead of writing mg, you can simply call it centripetal force. They want the centripetal force from the slope. So you say centripetal force divided by 4 pi squared m is equal to the slope. You find the centripetal force. And I think eventually they want you to compare it to part 1 because already you have it. And then compare means find the percentage difference. Let me write it down. Compare means find the percentage difference. And comment means list the sources of errors. Okay? And that's it. I know it sounds a bit difficult probably. Let us see the video quickly. I'm gonna insert my screenshot before I move to the video on a blank document. So insert picture from file, our final screenshot. Does it fit? It should fit. Yes, we can fix it later. Just make it central. All right, now let me fetch the video for us. I think it's here. No, I don't know where it is. It's here. Yes, I'm not gonna play it. I actually want to fast forward it. It will show you the different things. Probably I'm gonna pause a bit to explain. Let me just, yeah. So this is the central post. You see the spring, the orange indicator, the black level, and you have a pulley like wire, pulley, object, you have another pulley, and you have hanging masses. I'm explaining in the video, and you can listen to it later, how I attach the different wires and how I want my wires to be horizontal and vertical. This is the hanging mass, by the way. All right, how I create the perfect support, and I'm actually showing the orange indicator, how I pull the black up until I reach the orange indicator, because this is for me as a reference. Here, by the way, my system is not vertical, you see? It has a certain angle, probably because I moved a bit the masses in my hand, using my hands. So I'm gonna fix it to make it horizontal and vertical. Now it's perfectly horizontal, and here I'm moving the black indicator to hit the orange indicator. So now I'm not gonna remove the pulley. You see the pulley? So what I don't like about the video, this side is not showing, but my phone is not functioning properly, and I didn't know it was happening. So here I'm gonna rotate. Probably you can watch the video. You can see that most probably my system will move out of the circle a bit. It depends on speed of rotation. If my rotation is fast enough, probably my system will move away from the center even more. So I should not be too fast, neither too slow. I should be fast enough for the system to move a bit where it was initially positioned. So to be able to tell how can I create a certain rotation to mimic exactly the same amount of Newton I had initially here, is to look at my orange indicator. You see, the orange indicator is a bit higher than the black position. So I'm gonna use my system, like grab it from here and move it in such a way that my orange indicator is not too low and not too high. And my system is fast enough to have my orange indicator on the black level, all right? So you can see that I shouldn't go too fast, neither too slow, to have this equilibrium. Meanwhile, your partner should be taking measurements. What is the exact measurements you need in here? You need to know the average speed of rotation, the average. Did you hear that? Average speed. And average speed means total distance over total time, or the distance covered during one cycle over the time during one cycle. Because you can see you need an average. This keeps on moving up and down, meaning that the speed is not constant. And this is a human error. And I'm showing you throughout the experiment how I change the radius. You see here the big change in the position of the orange indicator and the black position. And I'm showing you how I move the black position again and how I do the experiment. Like here, I need to go really fast for the orange to go down. Let me see if it works. So should it be too fast or too slow? I'm gonna grab the system from here and start the motion. The orange indicator should go down to the black level. So this is too slow. Faster, 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 faster. So I'm getting slower. And whenever you reach the black indicator, make sure you maintain a constant speed, or at least if oscillation is happening, let it be around the black terminal, the black position. So now I'm gonna ask your partner or a partner to time how fast your system is going. So it could be like how long or what is the time needed to complete 10 rotations. How do I find the angular speed? I can do angular speed is 2 pi times 10 rotations divided by the time. So you can tell directly the angular speed needed. If you want to find the linear speed, you take the angular speed and you multiply it by the radius of rotation. How you can simply do speed is distance over time, exactly like what Carl stated. So the distance is 2 pi r, the circumference over time. So that's it, you guys. I'm gonna share with you this PowerPoint. Let me save it. and I'm gonna share with you the video and some results, and you do the thing. I'm gonna also give you deadline. It's gonna be Monday evening most probably, okay? Yes?
Doctor, it's Monday evening after the session, yes?
Yes, because I always want you to ask some questions during the session.
Okay.
And if you want my deadline to be different, just let me know. I'm ready for this. All right, so let me simply stop the recording.